Hi everyone, and welcome to the Chapter 14 lecture on correlation and regression. We're moving this chapter up because it tends to be helpful to talk about correlation before we talk about experiments. This lecture is broken up into two parts. In part 1, we'll talk about the basics of correlation and how to calculate a Pearson correlation. And in part 2, we'll talk about the interpretation and regression. Starting out, a correlation is a statistical technique that is used to measure and describe a relation between two variables. Essentially, we are asking ourselves, how related are these two things? This word related is important for two reasons. First, we are only talking about whether or not there is overlap between two variables. We are not saying whether one variable causes change in another. And two, we are not using the word relationship because a relationship implies personal connections. Relationships are for people and relations are for data. Further, when we are talking about correlations, we are typically observing a naturally occurring relation. We aren't doing anything to affect the data, we are just observing. Therefore, we are typically grouping correlated variables with descriptive statistics. If you recall, descriptive statistics simply describe the data as opposed to making inferences about the data. So this might mean that we look at the distribution with a graph, examine measures of central tendency, or look at measures of variability. Because we are looking at the relation among variables, correlations require two scores for each individual. They will have a score for X and a score for Y. We plot this using a scatter plot, which graphs pairs of scores and allows you to see trends in the data. The example on the screen shows earnings on the y-axis as a function of age on the x-axis. And you can see that generally, as age increases, earnings increase as well. To make a scatter plot, you simply put a dot or point for each pair of scores. For instance, this person, who is 20 years old, makes about $60,000 a year. The nice thing about scatter plots is that unless you have a reason to view the data in a certain way, such as with looking at age over time, the x and y axes don't really matter. You can have either variable on either axis. There are three characteristics of a correlation which we'll talk about: the direction, the strength, and the form. Starting with the direction of the relation, there are positive and negative correlations. Positive correlations have variables that trend in the same direction. This means that people who have high values on one variable also have high values on another variable. But this also means that people who have low values on one variable also have low values on the other variable. A negative correlation has an inverse relation among variables. This means that people who have high values on one variable have low values on another, or vice versa. People who have low values on one variable have high values on another. Students do tend to mix these up, so be sure to know the difference between them for exams. Here are two scatter plots with hypothetical data. The one on the left shows a positive correlation between the amount of beer sold and temperature. And you can see that as temperature increases, beer sales increase. On the right, we have a negative correlation between the amount of coffee sold and temperature. As temperature increases, coffee sales decrease. You might be wondering about the line that goes through each graph. These are called trend lines and they give you a better sense of the relation, but we'll come back to that later in the chapter. For now, let's relate this back to the last slide on directionality. Starting with the positive correlation, let's look at the most extreme scores on either end of the graph. You can see that when the x value is high, the y value is high as well. Likewise, when x is low, y is low. Again, this data trends in the same direction. Again, comparing this to the negative correlation, you can see that a low score on x means a high score on y, whereas a high score on x means a low score on y. Again, negative correlations have an inverse relation between x and y. We also have to consider the strength or consistency of a relation. Correlations are measured on a scale from 1 to -1, where either end of the scale is a perfectly straight line. A correlation of 1 or -1 is really rare in research, and a correlation of 0 means that there is no relation at all. Given that a correlation of 1 or -1 is rare, most correlations fall between 0 and 1 in either direction. You can see that a correlation of 0.5 shows some trend, but the scores are spaced out. But as you start to get closer to 1, the correlation becomes stronger. With this, it's important not to confuse direction with strength. You can see that a correlation of -1 is stronger than a correlation of positive 0.9. Additionally, correlations can only be between 1 and -1. You can't have anything beyond these numbers. So if you do calculate something greater than that, the calculation is incorrect. Lastly, we have to consider the form of a relation. In this class, we will only be examining linear relations, which means that we can draw a straight line through the data. However, you should know that nonlinear correlations exist and can be found in research. You'll likely learn how to calculate nonlinear correlations if you take future stats courses. With this, let's jump into how to calculate a correlation. We'll use this example from the textbook, examining hours slept last night and happy mood measured on a scale of 0 to 10. If we were to create a scatter plot of this data, this is what it would look like. It has a general positive trend. But the question is, how strong is this correlation? We'll solve this by running a Pearson correlation, which is one of the most common types of correlations. There are other correlations out there, but we'll stick with Pearson for this class. To find a Pearson correlation, we need to work with the variables of interest, x and y, separately. In this example, we'll have x be sleep and y be mood. First, you'll need to find the sum of squares for x. As a quick refresher, you find the sum of squares by taking the mean, subtracting the mean from each score, which gives you the deviations, and then squaring and totaling those scores. You can also review Chapter 4 if you need a more thorough refresher. Once you find the sum of squares for x, you also need to find the sum of squares for y using that same process. Once completed, you will take each of those deviations you found for x and y, multiply them, and then add them together. This is called the cross products, and I'll show you what this looks like in a moment. Once you have the numbers for steps 1 through 3, you can plug them into the Pearson correlation equation, which looks a little scary, but it's not as bad as it looks. In the numerator, we have sigma, which means sum, in parentheses, x minus the mean of x. The subscript here is just so you can differentiate what mean goes where. This is multiplied by y minus the mean of y. And if you notice, the score minus the mean is just the deviation, which is a step in finding the sum of squares. So this is the deviations for x multiplied by the deviations for y, which is the cross products we'll learn to calculate in a moment. In the denominator, we have the square roots of the sum of square deviations. In other words, this is the sum of squares of x multiplied by the sum of squares of y. So again, this is a very busy looking equation, but these are all calculations you've already been doing. If it's helpful, you can simplify this and just say cross products divided by the square root of sum of squares for x times the sum of squares for y. With those steps in mind, let's calculate the correlation for sleep and mood. We were provided a sample of 6 scores for sleep, which are shown here. Because we're just calculating and not comparing numbers in rows, the data do not need to be in numerical order. What we need to do is calculate the mean, which in this case is 7. And again, mean subscript x just means the mean of x. We then find the deviation by subtracting the mean from each score. As a reminder, deviations should always total to 0, so that's a good check at this point. We then square each value and total them, which in this case equals 16. Next, we do the same for y, which is mood. The mean is 4, so we subtract 4 from each value and then square and sum those numbers, which is 22. And now we're ready to calculate the cross products. As you can see, we need to take the score for x and subtract it from the mean for x, then multiply it by the score for y minus the mean for y. So first, let's identify our means. We have 7 for sleep and 4 for mood. So going down the list, our first scores are 7 and 4. So 7 minus 7 times 4 minus 4 is 0. Next one's down, we have 5 and 2. 5 minus 7 times 2 minus 4 is 4. Next one's down, we have 8 and 7. 8 minus 7 times 7 minus 4 is 3. Then we have 6 and 2. 6 minus 7 times 2 minus 4 is 2. Going down again, we have 6 and 3. 6 minus 7 times 3 minus 4 is 1. And lastly, we have 10 and 6. So 10 minus 7 and 6 minus 4 is 6. So from here, we sum all of these numbers, which gives us 16. So this is a condensed graph showing just that last row of the table to save space on the slide. From here, we can plug our numbers into the correlation equation. Remember, we need the cross products and the sum of squares for each variable. This gives us 16 divided by the square root of 16 times 22, which is 0.853. Here is another example for you to try on your own. Find the correlation for marital satisfaction and overtime hours worked. Pause to solve. The answer will be shown in 5 seconds. Here is what your table should look like. The mean of x is 6. The sum of squares of x is 80. The mean of y is 9. The sum of squares of y is 456. And the cross products is negative 164. Using the correlation equation, that gives us negative 164 divided by the square roots of 80 times 456. Which gives us negative 0.859, which is a pretty strong negative correlation. This is what the scatter plot would look like if you were to plot it. And that is the end of part 1 of the lecture. Please let me know if you have any questions.